So when we defined linear transformations, we saw a lot of matrices coming in as examples of linear transformations. In fact, we saw that any m cross n matrix can be thought of as a linear transformation from Rn to Rm, and it was vaguely hinted upon that we can associate a matrix to any linear transformation in the right setting. So in this video, we will try to make precise what is meant by a matrix associated to a linear transformation when what is called as the coordinate bases are specified. So let's begin this video by defining what a coordinate basis is. So let's define what coordinate bases are. So let's focus our attention on finite dimensional vector spaces here. So let V be a finite dimensional vector space. Needless to say, all our vector spaces are over the real numbers. So let beta, okay, let's not define it that way. We say that a sequence of vectors, let's call those vectors, sequence of vectors as v1 to vn. We say that a sequence of vectors is a coordinate basis. Let's also give the alternate name to it. It is also called an ordered basis if the sequence forms a basis of V. So let's just try to understand what this definition says, because it doesn't seem like it says much, but that's not the case. We start off with a set, say V1, V2 up to Vn, which is both linearly independent and a spanning set. It turns out to be a basis. When we speak about an ordered basis or a coordinate basis, we are concerned about the order in which we are considering the basis elements. So, in this particular definition, you should observe that we are always considering a sequence of vectors v1, v2 up to vn. So, in other words, we can talk about the first vector, the second vector, third vector, nth vector, and so on, which we couldn't have done when we just talked about a basis, because there was no inherent order which we were referring to in the definition of a basis. So, from your knowledge of real analysis, you would realize that if two elements in a sequence are interchanged, the sequence has technically changed. So, that is exactly what will reflect here as well. So, if the order in which we consider the basis change, the coordinate basis changes, even though the vectors needn't have changed. So, let us give a few examples to illustrate all that we just saw. So, examples. The simplest example should be in, say, R. Let's go to R3. R2 will be too simplistic to talk about the change in order. So, in R3, let beta be the, so sometimes the Greek alphabets are used to denote ordered basis or coordinate basis. So, beta, let this be the sequence of vectors 0, 1 0 0, 0 1 0 and 0 0 1. From whatever we have seen till now, we know that the vectors 1 0 0, 0 1 0 and 0 0 1, they form a basis, and in this order beta is a, then beta is a coordinate basis of R3. As pointed out just a couple of minutes back, if we change the order, let beta prime be a new collection or new sequence which is obtained by, say, interchanging the first and the second vector. So let this be 0 1 0 1 0 0 0 0 1. Then beta as a set, the collection of these three vectors are no different from the collection of vectors which we get from beta. However, we are not just looking at it as sets, we also do have an order of the vectors that is being considered in mind, and therefore beta prime is a coordinate basis. It's not just a coordinate basis, it's a coordinate basis which is different from beta. We just change the order and we still treat it as a different ordered basis. So why are we doing all this? So this doesn't seem like a property which we should keep notice of with so much care. That's how it might sound at the first sight. However, what we will see now will illustrate that there is a reason why all this is being done. So this is a coordinate basis. So let's also now look at what is a coordinate vector corresponding to a with respect to a basis, a coordinate basis. And then we will proceed. Coordinate vector with respect to a coordinate basis. So let V, again the same setup as above, V be a finite dimensional vector space. Let's say it's of dimension n. So, and let beta be equal to V1 to Vn be a ordered basis or a coordinate basis. So ordered basis is an equally popular term in literature. Of capital V, a finite dimensional vector space. Then every vector in, so let V, so let small v be a vector in capital V, and by one of the results we have proved earlier, we know that every vector in capital V can be uniquely written as a linear combination of V1, V2 up to Vn. Then by a result proved earlier, V can be written as Va1 V1 plus dot 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 An Vn uniquely for some scalars A1, A2 up to An in R. Then we say that the column vector A1 dot 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 up to An is the coordinate vector or coordinate representation of V with respect to or relative to beta, and is denoted T, sorry, there is no T, V and a superscript beta. So the moment we have a ordered basis. So, there is a V1, V2 up to Vn in that order. Then because it is a basis, we will be able to write V as a unique linear combination of V1, V2 up to Vn, and let us say this is the linear combination that we have, A1 V1 plus A2 V2 plus up to An Vn. And the column vector A1 to An is called the coordinate vector of V relative to the coordinate basis beta, and its notation is this V beta. Example. Again, let us go back to the example we have been considering. Let beta be equal to, let me write it as E1, E2, E3 for the standard basis, be an ordered basis. Of R3. Recall that E1, E2, E3 are vectors with 1 in the, say for E1 it is 1 in the first coordinate and zeros in the other coordinates. Ej similarly is always defined as 1 in the jth coordinate and 0 in the remaining coordinates. So, if it is in R3, we are looking at 3 tuples, 3 vectors, or 3 coordinates rather. So, consider a vector V. Let us arbitrarily take vector V and let us look at the vector 1, 2, 3, the simplest vector that we can, not the simplest vector, but a very simple vector. What is V in terms of E1, E2, E3? V is then equal to 1 times E1 plus 2 times E2 plus 3 times E3. This is our V as a unique linear combination of the standard basis, and therefore, V beta is represented by 1, 2 and 3. Suppose we change the order, let beta be equal to E2, E1 and E3 like we had done earlier. Then what do we know about V? Then V, so let us call now this to be F1, let us call this F2 and let us call this F3. Then V is equal to 2 times F1 plus 1 times F2 plus 3 times F3. I have just changed beta to beta prime here because beta was already taken. Then our coordinate representation, coordinate vector of V with respect to beta prime will then be given by 2, 1, 3. Note that this and this are not the same. So, the columns which represent our given vector with respect to the two coordinate bases have now changed, and that is the main reason why we are interested in the order. The order is not the only thing that might change. For example, what is the vector we started off with? It was 1, 2, 3. Now, let us complete 1, 2, 3 into some bases. It will certainly have 1, 1, 0, 1 and 1, 1, 0. These 3 you can check is a basis for sure in this order. Let us consider gamma to be in this order. Then check that gamma is a coordinate basis, not just a basis, not just a spanning set, it is also linearly independent. If it is not needed to check both, because it is a set which contains 3 elements in a dimension 3 vector space, and therefore, if it is either linearly independent or linearly or a spanning set, it will be a basis because the other will be naturally satisfied then. Right. So, V can then be written as, then again check that V, which is our 1, 2, 3 is nothing but, so let us call this EF, let's call G1, this is G2, and let us call this G3. I should have just called it V1, V2, V3, it doesn't matter anyway. This is going to be 1 times G1 plus 0 times G2 plus 0 times G3, and therefore the vector V is, in terms of this gamma, the coordinate vector of V relative to the coordinate basis gamma will be nothing but 1 0 0. So as you can see, based on the choice of our basis, the coordinate vector of the given vector with respect to the basis will turn out to be quite varying, actually, quite varied. In this case, it was 1 2 3, it was 2 1 3. In the second case, when we picked gamma to be 1 2 3, 1 0 1 and 1 1 0, it turned out to be 1 0 0. So it changes quite a lot. So the order and the basis does contribute a lot. The order of the basis does contribute a lot. So let's look at more examples. Another example. So coordinate basis is a simple way to have more complicated vector spaces expressed like in the case of Rn. So this following example will indicate that. So let Pn of R be the polynomial ring of degree less than or equal to n with coefficients in R. Be the polynomial vector space of degree less than or equal to n. And we know a particular basis for this particular vector space. Let beta be 1x x square to x to the power n be a coordinate basis. So in this particular order, if you consider, it's a coordinate basis of Pn of R. Let P of x be some polynomial. Let's say this is x square plus 2x plus 1. Then P of x will have a coordinate representation, coordinate vector of P of x with respect to beta will just turn out to be equal to 1 2 1 0 0 dot 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 0. The n plus 1 cross 1 vector in the right here. This is the coordinate vector of P of x with respect to it. Let's just make it a bit more simple. Let us focus on n equal to say 2. Focus on P2 of R. Then P of x beta will just turn out to be equal to, what was our P of x? X square plus 2x plus 1, and beta, if it is 1x x square, this is going to be x square plus 2x plus 1 will be 1 2 1. Okay, let us now consider q of x to be equal to 4x square plus 3x plus 2, some other polynomial. That's a symmetric polynomial. I don't want to work with, it's a symmetric looking polynomial, at least with respect to this basis. What is q of x with respect to our beta? This is 2 3 4. You should check this out. Now beta, there is no natural order in which we should be considering these vectors. What if let beta prime be the polynomials x square x 1 in this order, basically the reverse order as in beta. This could also have been the order in which we started looking at the basis. And then what would be q of x with respect to this beta prime? The coordinate vector of q of x with respect to beta prime will just turn out to be equal to 4 3 2. So as you can see, again, this also illustrates, this example illustrates two things. One, that P of x can be realized as something like Rn given a coordinate basis. Once you fix a coordinate basis, you can then represent every element or every vector in Pn of x as a vector, as a coordinate vector, which is a column vector. And the second thing is that, again, if you change even the order in which the basis elements are being considered, the coordinate basis changes and the entire representation changes. So everything is once we fix a basis. All right. Okay, so we have spent some considerable amount of time trying to develop the concept of a coordinate basis. Now let's move over to what is meant by a matrix which can be associated to a linear transformation. So matrix associated to a linear transformation. So let V and W be finite dimensional vector spaces. Dimension of V be say equal to n and dimension of W be equal to m. And let's also fix some ordered basis here. So, and let beta equal to V1, V2 up to Vn be an ordered basis. Let me use the word ordered basis just for the sake of familiarizing that term. It is the same as a coordinate basis of V and gamma, which is a W1 to, if it is an m dimensional vector space, there will be m vectors in every basis. So let gamma be an ordered basis of W. Okay. Further, let T be a map from V to W, which is a linear transformation. Let T from V to W be a linear transformation. So now we are curious about what would be the way in which the coordinate vector corresponding to a vector V in capital V and the coordinate vector corresponding to TV in capital W with respect to gamma, how will they interact with each other? That is the question we would like to ask. Let's write down the question more specifically. Let V be an arbitrary vector. Let fix a vector V in capital V. Then every vector has a coordinate representation. So the coordinate vector of V with respect to beta, let it be equal to say something like x1 to xn. In other words, this, okay, we'll come back to that. This is just telling us that V is x1 v1 plus x2 v2 plus xn vn. Let TV with respect to gamma, again the coordinate vector of TV remember is a vector in W and gamma is a coordinate basis here, coordinate basis in capital W of m vectors. Then this will be a column vector of size m cross 1. So let this be denoted by say something like y1 to ym. We would like to know how is the column vector x1 to xn related to y1 to ym. So we would like to explore how the column vector y1 to ym and the column vector x1 to xn are related. Clearly, the relationship has to be through our given linear matrix, linear transformation T. So let's look at that again. So V with respect to beta being equal to x1 to x1 implies, this is an if and only statement, V is equal to x1 v1 plus x2 v2 plus up to xn vn, right? We also know that TV is y1 to ym with respect to gamma, and that tells us that TV is equal to y1 w1 plus y2 w2 plus up to ym wm. But we know that with respect to a given basis, the represent the linear combination of the bases will be unique to give us the vector TV. So if we can realize TV as a linear combination of w1 to wm in some other manner, the coefficients have to be equal component wise. So let's just give the first one a name star. Star, when we apply T to star, star gives us the following. TV is equal to T of the right hand side, which is T of x1 v1 plus up to xn vn. But recall that T is a linear transformation, and this will just turn out to be T x1 times T v1 plus up to xn times T vn by the very properties of linear transformation. But then each of these TVIs are vectors in capital W. So let's just write it down as a linear combination of the vectors w1 to wm, each of them. So this will just turn out to be equal to x1 times, let's write tv1 in terms of the vectors w1 to wm. So this will just turn out to be a11 w1 plus a21 w2 plus am1 wm. Observe that the second index corresponds to v1 and the first index corresponds to the running w1 w2 up to wm. Similarly, tv2 can be written as a12. Remember that this is corresponding to the second index is corresponding to the vector v2. So this is, and the first one corresponding to w1. So this is going to be a22 w2 plus am2 wm, and x3 can be written similarly. Finally, xn times the first vector, again remember the first index is corresponding to w1 and the second one corresponding to vn. So this will be n, w1 plus dot 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 amn wm. This is what TV can be, this is how TV can be written as. So where, let me just write down, TVJ is equal to A1J W1 plus dot 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 AMJ WM. Each of the Vj can be written like this. Let me just maintain this because now we can rewrite this. Therefore, TV, if you observe carefully after rewriting, this will just turn out to be in terms of what will be the linear combination above in terms of w1 w2 up to wm. If you observe carefully, this is x1 a11 plus x2 a12 plus xn a1n times W1 plus x1 A21 plus x2 A22 plus xn A2n times W2 plus dot 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 x1 A m1 plus x2 A m2 plus xn A mn times Wm. I have just rewritten the above in terms of coefficients of W1, W2 up to Wm. This is something which you should check. Just rewritten it down. And therefore, TV of gamma remember was W1, W2 up to Wm. This just can be written down as x1 A11 plus x2 A12 plus xn A1n dot 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 xn Amn x1 A11 plus x2 am2. I am making some unnecessary mistakes. This will be m1 plus dot 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 xn amn. And remember that this was nothing but y1, y2 up to ym. And there we have. The right hand side looks quite cumbersome, but if we are to recall our knowledge of how matrices multiply, we can write this as, this is the matrix multiplication of A11, A12, A1n, AM1, AM2 up to AMN. This times x1 up to xn. So this is exactly how the coordinate vector of TV corresponding to gamma and the coordinate vector of V corresponding to beta are related. It is related by a matrix multiplication. So this matrix, as you can see, are having entries of what are if you recall, Aij's were the coefficients of TVI in terms of Wj. The image of the vectors in the coordinate basis of V when written in terms of the coordinate basis of W gives us this particular matrix. So we denote or we call the above matrix. Okay, let me think about how to put it in words. Okay, the above matrix is called the matrix of the linear transformation T with respect to beta and gamma. Matrix of the linear transformation T. Observe that this matrix very heavily depends on what beta and gamma are. So it's a linear transformation T with respect to beta and gamma. As I just mentioned, each of the coefficients here are obtained by writing TVJ in terms of W1 to Wm for each of the j going from 1 to m. And this is also denoted T beta, gamma. So the notation we are following has a name. It's called the Einstein convention, which is used by physicists extensively. Let's not go into that, but this is the notation. Okay, so we have defined what the matrix of linear transformation is when the coordinate basis of the domain and the range are specified. Remember that there is this dependence of beta and gamma extensively. This matrix will not make sense if we don't mention what the coordinate bases are. So let's look at a couple of examples. The example above would be, okay, example, it will be a good exercise to go back to our various examples of linear transformations. Pick your favorite basis on the left and a favorite basis on the right, or in other words, a favorite coordinate basis of your domain and a favorite coordinate basis of your range, or rather the target vector space, and compute the matrix of the linear transformation with respect to the various bases you pick. You will see that the bases can look the matrices can look very different. We will see how they are all related later, but right now let's again look at one or two examples. One example which I would like to very easily pick and show is the differentiation operator, which is from P3 of R to Pt of R. Let D be the linear transformation where D of P of x is equal to P prime of x. So what do we know about P3 of R and P2 of R? We know that P3 of R is 4-dimensional, P2 of R is 3-dimensional. We also have at least the knowledge of one coordinate basis here. So let beta denote the coordinate basis here, which is given by 1x, x square and x cube. Let gamma, so this is 1x, x square. They are looking like similar polynomials, but they are polynomials in different vector spaces. Be coordinate basis in P3 of R and P2 of R respectively. So one point I would like to note here is that each of the columns, if you observe carefully, turns out to be the coordinate vector of TV. So this is the coordinate vector of TV1 with respect to gamma. This turned out to be the coordinate vector TV2 with respect to gamma. This turned out to be TVN with respect to gamma. So observe, let me add something here. Observe that T beta gamma is nothing but this particular matrix where the columns are TV1 with respect to gamma, TVN with respect to gamma. So this is an M cross N matrix. So the columns turn out to be the coordinate vector of the basis vectors from the coordinate basis of beta of V mapped to W and written in terms of a coordinate basis in W. So to write what the matrix of D, so then the matrix of D with respect to beta and gamma can be obtained by looking at what is D of each of the coordinate basis vectors by looking at what is D of the vectors in the coordinate basis beta by observing D of V where V belongs to beta. So you can check that D1 with respect to gamma is 0, 0, 0. The constant is always killed by the differentiation. Dx is equal to 1, 0, 0. Dx square is equal to the derivative of x square is 2x, which is 0, 2, 0. And what is dx cube? This is going to be equal to 3x square, which is 0, 0, 3. Thus, matrix of D with respect to beta gamma will be 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3. Let's now check that this representation indeed is working. So, for example, let's take an arbitrary polynomial. In fact, let's take the general polynomial of P3 of R. So, let P of x be equal to something like say A0 plus A1x plus A2x square plus A3x cube. Then what is P of x with respect to, so where is this? This is an element in P3 of R which has beta as its coordinate basis, which is 1x x square x cube, and this is going to be A0, A1, A2 and A3. Now what is going to be dP of x with respect to gamma from whatever we have developed so far? This is just going to be the matrix multiplication of the matrix above, this one, with the coordinate vector of P of x with respect to beta, and that will just be equal to 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3 times A0, A1, A2, A3, which is going to be A1 2A2 and 3A3, as it should be. It should be a 3 cross 1 column vector because we are ending up in P2 of R, which is a 3-dimensional vector space. And by the very definition, what is this? Let's check whether what we have got is right. This implies dP of x is equal to, this is with respect to gamma, which is A1 times 1 plus A2 times x plus 3A3 times x square, which exactly turns out to be our derivative of P of x. What is the derivative of P of x? It will just turn out to be A1 plus 2A2x square, sorry, 2A2x plus 3A3x square, which is what we have got here. So yes, so this does work. So many times the linear transformations that we are considering will not be so straightforward, and it boils down to looking for a good basis with respect to which matrices will be nice and easy to work with. That will be a major part of this course. So we will come to all that later. Right now, the key thing to keep in mind is that given any linear transformation, if we have a coordinate basis in the domain and in the target vector space between finite dimensional vector spaces, of course, then we can talk about a matrix corresponding to these coordinate bases, and the linear transformation from V to W will just turn out to be the matrix multiplication of this matrix with the coordinate vector representing our given vector V with respect to the corresponding basis, to get back the coordinate vector of TV with respect to the basis of the target vector space.